So good afternoon and welcome to the fifth weeks of the facilitations. So we are halfway done. So last week we are able to complete our discussion on geometry interpretations of complex functions. So this week we will be looking at analytical functions and see how this concept is being formulated and how to use them to solve some problems. So if you have been going through the course material that I sent last week, so our discussion today should be on this page, which is unit 2, which is analytical functions.
Sorry, sir. Sorry, sir. Hello?
Yes, I'm with you.
Yeah, since from the last time you mentioned course material, I tried to check through the mail. I
Okay.
didn't see
Yeah,
material.
I
I
sent
tried to check.
I sent it the first week of the lecture. That the first email that I sent it then. So if you don't have it, you can come to the course page. If you go to the course page, you should see it. I think I put it somewhere around this place. Or better still, I can still resend it again. Because I send it, if you check this email, sent messages. So I sent it, okay, around. So I sent it, this is the message, course lecture note. I sent it this period, that's September 6th.
Oh, okay.
So
Okay.
the title is course lecture note.
Okay.
So you can check your email.
Okay.
If you see something like this, course lecture note, I send it as a PDF. But if you don't see it, I can still resend it again anyway.
Okay. Okay, maybe, sir, if it will not be a bother to you, can you help me?
Yeah, I can resend it now before we go for the
Okay.
next, before we start the next class. So let me just send it to you straight. I will send it to all the students now, so you can have it again.
Okay.
Just wait. That was the first thing I did.
Oh, okay.
Upload file, browse. It should be here. So this is the lecture note.
Today we are only two of us. So.
Is that what?
I say it's only. It seems it's only me and you or
Yeah.
another student.
Some students have not been joining. They only go online to check the recorded this thing. But I cannot wait for them. We have a timeline.
Yes, yes.
So this is 313 lecture notes. They are all. That is the lecture notes. So I send it again. You should have it in your email now.
Okay, sir. All right. Thank you.
Yeah. Okay, sent. So if you check your email now, for example, if I check my email now, I should have it here in my email now. So you can see.
Yeah.
This is it in my. This is it. So you just click it. This is it.
Okay.
So you see it below in your email. Once you open the email, you see it. This is the file. Once you click on it, it will open the PDF for you.
Okay, sir. Thank you
okay?
so much.
Okay.
Yeah.
So now let's continue our class.
Okay.
So we are discussing analytical function. So the first thing is to define analytic functions and what that function is. He said a function f of z is analytic at a point z naught if its derivative f prime of z exists not only at z naught but at every point z in the neighborhood of z naught. What we are trying to say is that if you have a function, let's say for example, we have f of x is equals to, can you see my board?
Not clear. It's like this reflection
I want
of
to write
light.
something on the board. That's why I'm asking. Can you see the board?
Yes, I can see the board, but it's distance.
Can you see what I wrote?
The root L.
F, good. So if you have, let's say we have y is equals to 2x squared plus 2x plus 3. So this is a function which we can say is f of z. So if this z now, we can say z is equals to x. If you replace this now with z, we can now say y is equals to 2z squared plus 2z then plus 3. So this y now is same thing as f of z because it's a function. So we can write this as f of z to equals to 2z squared plus 2z plus 3. So if you take derivative of this, that is, you differentiate this, that is the f of z dz. This will give you 4z plus 2. So this is what we call f prime z. That is the first derivative of that function. Did you get it?
Sorry, sir. Can you take your camera close to the board?
Okay. So this now, this derivative now, this over this is equals to this, is what we call, is what is referred to as f prime of z in this in this definition. So if we now say that z is now equal to our z naught and it's equals to 2. So wherever you see z now, you put the value of z there, then you perform algebra on it. This is 4 times 2 plus 2. That is 8 plus 2. That is equals to 10. So this 10 now tells us that the function is analytic at that z naught. So our z naught in this case is 2. Do you get the concept now? So once you do that and you put the value into it and you are able to get a numerical value, then the function is said to exist. And the function is analytic at that point. Is that taken?
Yes, sir.
Okay, good. So one can show that if fz is analytic, the derivative of u plus u and v of all others exists and are continuous functions of x and y. So what I'm trying to say is that if you not have a kind of a function, you know, in this case now, the function that we have is just a function of y and z. If you now have z is equals to 2xy plus 3y plus 3x. Now you can see that we have multiple variables in it, x and y. So we can divide in this format, that this partial derivative of u as a function of x can be written in this format, that this squared v as a function of dx, because here now, this example, we have x and y as our variable. So which is equal to all this. And by the time you put this to equals to this, you can have it dx squared. You have a question?
No. Right on, it's my colleague that.
Yes, d square u of ds square plus d is equals to 0. This is a kind of an expression that can be used to simplify it, and it's called the Laplace equation. This is what they call the Laplace equation. This one. This expression is what we call the Laplace equation. This. Is that taken? So
yes,
thus both ux and y and vsy satisfy Laplace equation, which is this. So now the main content now is that the analytical function is an infinite derivative function such that the Taylor series at any point x naught is in its domain. like what you are seeing here as the equation is like what I've just solved on the board now. Just trying to take derivative of a function, put the value in, and you summarize it. So if you now come to, let's look at some definition now. Now there is this theorem that said if the derivative of f of z exists at point z, like we have here, then the partial derivative of u and v exists at that point and obey the following condition. There are some examples that we are going to look at later, and then you can understand it better. Du dx is equals to dv dy, and du dy is equals to minus dv dz. You need to master this expression for you to be able to solve some of this problem, and that is what we call the Cauchy-Riemann equation. So say let u and v be real and simple and single value function of x and y are called, which together with their partial derivative of the first order, that is the first derivative, not the second derivative. So we can now say that Cauchy-Riemann equation, which is f of z is equals to u of x plus y plus v of xy, be analytic in region R in such that u and v satisfy Cauchy-Riemann equations. What we are trying to say is that if you are given a function like this, what you need to do is that you first take derivative of that function with respect to x and with respect to y. So by the time you substitute it back in this Cauchy-Riemann equation and the Laplace equation, the result must be the same thing. We see a very good example here. Now look at this. Now this is an example. Say show that define that f of z is equals to exponential z is analytic in z, and that the ez dz is equals to exponential z. Now solution. Now you know that in a complex variable our z is equals to this, which has x and y. So in this case now, by definition, we are given this f of z is equals to this. So where you see z, we put, since we know that z is equals to this, so we replace z here with this expression. So that's why we have this. So with this now, our f of z is now equals to this. So we can use law of algebra or law of rules of logarithm to simplify this. Once we have plus here, it is multiplication. So we now have two separate quantity, e of s and e I y. So the whole of this is called the Euler formula. This one is called Euler formula, which can be written in this format. That's why you have this. So by the time you allow e of s to work on each of these, you now have them in separate form. For u, the first one without I will be this, and for the second one, which is v, which is this. So if you now take derivative now, to show that f is analytic, we verify Cauchy-Riemann equations. So you take this now, this is the first one, which is u. Then du dx, it is only this that is this is a constant. You have it as a constant. When you take derivative of exponential, it will still remain as that. That's why you have this. Then v now, the same thing. The v, the x, this is only this is a constant. By the time you take it, you also have the same thing. Now, if you now take derivative of u with respect to y now, this is y. When you differentiate cos, it will give you negative sign. That's why you have this. And when you differentiate sine, it will give you cos. That's why you have this. So we say that if you look at this expression here, that Cauchy-Riemann, in Cauchy-Riemann, this is the result you have for du dx must be the same thing as the result for dv dy. And the result you have for du dy must be the same thing as negative dv dx. So if you substitute those results now into it, du, what's our du ds? Our du ds is this. Then dv dy is equals to this. You see that this and this are the same thing. So that satisfies one part of the Cauchy-Riemann equation. Then we have du dy. This is our du dy, negative exponential sine y. Then our dv dx is this. But mind you, the expression has negative. You put negative there, so this and this are the same thing. So automatically, this satisfies this Cauchy-Riemann equation. So hence, f of z is equals to this is analytic. So we can also show that the f of this is equals to this expression. Just substitute in the value and you have this as your expression. Did you understand that?
Yes, sir.
Okay, fine. You can take your time to also go through it yourself and see how to simplify it very well. So if you have any problem with that, you can reach out to me, because that is just what we are expected to discuss this week. So because next week we are going to be looking at complex integral. So I don't want us to start that today, so that you can have time to look through this and understand how to solve the problem. Is that taking? Is that taking? Hello, Mr. Joseph. Is that taking? Okay. So if you don't have any questions, I would like to stop the class for today so that we continue next week. Thanks for coming.
Are you getting me?
Yes. So I'm about ending the class now.
Okay, my internet just went off a bit.
Yeah. So what I'm trying to say is that if you don't have any questions, I would like to end the class today. Try your time to go through the note I sent to you. Then if you have any problem, any challenge, get back to me. So next week we start complex integral. Is that okay?
Yes, sir. Thank you.
Thanks for coming.
All right, sir.